Hi friends, welcome to this session. Today we are discussing Lorentz transformation and derived the set of equations that is called as Lorentz transformation. Einstein proposed the special theory of relativity in 1905. The special theory deals with the problems in which one frame of reference moves with a constant linear velocity relative to the another frame of reference. Einstein drew a very important conclusions. These two conclusions are called the fundamental postulates of the special theory of relativity. These postulates are: first, all physical laws are same in all inertial frame of reference that are moving with constant velocity relative to each other. And the second postulate is the speed of light is same in the vacuum in every inertial frame. According to the first postulate, it is impossible to demonstrate absolute motion, the motion with respect to ether. The motion of a body relative to ether has a physical meaning. According to Einstein, there is no absolute motion. Einstein did not completely reject the idea of ether. But according to him, ether can never be detected. Einstein reasoned that if we were alone out in space and far removed from all the stars and planets, so that there is nothing to use as a reference point to measure one's speed, we never know whether we are moving or not. But if two persons are in the space in two smoothly and uniformly moving rockets, when they are apart from each other but in the range of visibility, then they are able to say whether they are moving or at rest by comparing their positions. And according to the second postulates, light travels with the same speed in all directions. Here, no source of light can be treated as moving or stationary. Whether the velocity of light is measured relative to the medium in which travels relative to the moving observer. The second postulate can be proved by the Michelson-Morley experiment, and the theory based on these two postulates is called special theory of relativity. On the basis of Einstein's postulates of a special theory of relativity, Lorentz derived algebraically the transformation that has replaced Galilean transformation and also agrees with the Michelson-Morley experiment, and derived the set of equations are called as Lorentz transformation. For the sake of our convenience, let us consider the two frame of reference S and S dash. S is at stationary and S is in motion with a constant uniform velocity relative to S frame, and the motion is along x direction. The two observers O and O dash observing the event is happening here. For the convenience, let us consider that x-axis of the two systems coincide permanently. Here, both the frame of reference or these two x-axis are coincide permanently, and the velocity is parallel to the x-axis of two systems. The event is P, a light signal, and is produced when both this T and T dash are 0 when the origins of the two frames coincide. The event P is determined by the coordinate x, y, z and t for the observer O, And the for observer O dash, it is x dash, y dash, z dash, t dash. The light pulse produced at t is equal to 0 and will spread out as a growing sphere, and the radius of wavefront produced in this way will grow with the speed c. C is the speed of light. Since x, y, z, t are the coordinates of the event that is relative to the S frame which is at rest, and that coordinates are observing by the observer O in the S at rest. Therefore, the equation of the spherical surface whose radius is equal to r is equal to ct and grows at the speed c. So we can write x square plus y square plus z square is equal to r square. For the reference, frame of reference, yes. Similarly, for the frame of reference S dash, we can write x dash square plus y dash square plus z dash square is equal to r dash square. So we can write these two equations and derive the Lorentz transformation set. So for the first frame of reference, we can write that is the x square plus y square plus z square is equal to r square. Just rearrange it. R square goes to this side, so x square plus y square plus z square minus r square is equal to 0. So we know the value of r, that is the ct. So we can write x square plus y square plus z square minus c square t square is equal to 0, referred as equation 1. Similarly, we can write for the frame of reference 2, that is the x dash square plus y dash square plus z dash square minus c square t dash square is equal to 0. So we can write the equation 2. So equation 1 and 2 must be equal since both the observers are at rest. The center of the same expanding the wavefront initially. So we can write the equation that is the x square plus y square plus z square minus c square t square is equal to x dash square plus y dash square plus z dash square minus c square t dash square. Since there is no motion along the y and z axis, so we can write y is equal to y dash and z is equal to z dash for the symmetry. Now equation 3 can be written as, or it becomes by comparing the two equations, that is the first and second. So we get x square minus c square t square is equal to x dash square minus c square t dash square, and we get the equation that is the x dash is equal to gamma x minus vt. So gamma is nothing but, for the sake of convenience, we are relating these two equations for the transformation equation relating to x and x dash. So just put the value, that is the x dash is equal to gamma x minus vt is independent of x and t. So the reasons for trying the above relations are: first, on the basis of the first, that is the transformation must be reduced to Galilean transformation for the low speed, and that speed is v by c tends to 0. And second, the transformation must be linear and simple. So we see that the relation is sufficiently general to satisfy the required condition. And since the motion is relative, we assume that S is moving relative to S dash with a velocity v along x direction, positive x direction. Since we can write for the frame of reference S, x is equal to gamma in bracket x dash plus vt dash. So putting the value of x dash from equation 3, from equation here we derived all these 6 equations. Now putting the values of x dash from equation 6, so we can write x is equal to gamma into gamma x minus vt plus vt dash. So just rearrange it, x is equal to gamma square x minus vt plus gamma vt dash. Then we get t dash is equal to, So here it is t dash. So the just we are simplifying it, and t dash is equal to gamma into t minus x by v plus x by gamma square v. Just rearrange it. So we get this value, that is the t dash is equal to gamma int bracket t minus x by v 1 minus 1 by gamma. So it should be by squaring it on both sides. So putting the x dash from equation 6 and t from equation 8. So we get just these are the simplification. So x square minus c square t square is equal to gamma into x minus vt whole bracket square. Then just subtract it, minus c square in bracket square bracket x gamma in bracket t minus x by v, in parenthesis we can write 1 minus x by v square. So whole bracket square is there. So by solving we get this equation. Then after rearranging we get the equation number 9, that is the x square minus c square t square minus gamma square in bracket x square minus 2v txt plus v square t square bracket close plus c square by c square gamma square. Likewise this equation we get. So the equation 9 is, this is equation 9, is identity. The coefficient of various powers of x and t must vanish separately, and equating the coefficient of xt to 0. So we get this equation. Again we are rearranging it. We get this equation. By solving we get v square minus c square into gamma square plus c square is equal to 0. So now putting the coefficients, that is the c square is equal to 0. So we get the r square v square minus r square c square plus c square is equal to 0. So we get this equation. Then we know that the gamma is nothing but 1 divided by under root of 1 minus v square by c square. So putting this value in equation this, which that is the gamma is equal to 1 by under root of 1 minus v square by c square. This is value. So now by putting this value we get x dash is equal to x minus vt divided by square root of 1 minus v square by c square. So 1 by square root of 1 minus v square by c square is the gamma. Now putting this gamma in equation number 8, so we get, so this equation. By rearranging and solving we get this equation. Again by simplifying all these steps we receive the t dash is equal to t minus vx by c square whole divided by under root of 1 minus v square by c square. So this value, with the help of this x dash and t dash, we get y dash is equal to y, z dash is equal to z. So we get all these 4 equations, and this set of equation is referred as Lorentz transformation. The equation gives the Lorentz equation, Lorentz transformation equation. If the system S is moving with relative to S dash. Now in the first case we say that the S is a stationary and S dash is in motion relative to S. Now we are saying that if the system S is moving with velocity v with respect to S dash, we get the inverse Lorentz transformation equation by putting minus v in a place of v and interchanging the primed and unprimed quantities. Thus the inverse Lorentz transformation equations are, just put the value x dash, in place of x dash we write the x, in place of x dash we write the x, and so we are changing the minus v to plus v. So you can write x is equal to gamma into x dash plus vt dash. By changing y is equal to y dash, z is equal to z dash, and t is equal to gamma into t dash plus vx by c square. Now the superiority of the Lorentz transformation over Galilean transformations are, just compare all these equations. Which one? This with the Galilean transformation, and if we say that if is far less than c, then v by c is also far less than c. Therefore Lorentz transformation reduced to x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to t. So we vx by c square is far less than t. So above this equation, that write the x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to t are the Galilean transformation. Thus for the low values of the velocity v, the Lorentz transformation approaches to the Galilean. Thus we can say that the Lorentz transformations are hold for all velocities, while Galilean transformation hold only for low velocities. Consequently, the Lorentz transformations are superior to Galilean transformation. So these are the Lorentz transformation comparing with the Galilean transformation, and I hope you understand the set of Lorentz transformation and the Galilean transformation and comparison between the two transformation. So I hope you understand all these things. So thank you very much for watching this video.